In this lecture, we are going to discuss confidence intervals. So far, we've looked at various statistics on the return, such as its mean, variance, skewness, and kurtosis. Whenever we estimate something, we also want to ask, how confident can we be in that estimate? Generally speaking, the more data you collect, the more confident you can be. So when you have more data, your confidence interval will become smaller. When you have less data, your confidence interval will become larger. This lecture is not meant to be a rigorous derivation of confidence intervals, but rather just a bit of mathematical intuition only. Before we dig into confidence intervals, I want to discuss why this might be of interest in the context of finance. Again, we are interested in the return, and specifically the expected return. You've seen that one way we can estimate the expected return is to calculate the sample mean. Suppose we get a number bigger than 0. You might automatically assume this is a great stock. Its expected return is above 0, and therefore I will make money if I invest in this stock. However, keep in mind that this is only an estimate. What if we were to also include a confidence interval on that estimate? And what if we find that this confidence interval contains negative values? In this case, we can't rule out that the expected return could actually be negative and not positive. So the rest of this lecture will focus on how confidence intervals actually work and how we can compute them. To start, we have to establish that our sample estimate of the expected return is random. That is to say, it's a random variable. Obviously, it's not as random as the result of a coin toss, but it's random nonetheless. Recall that the sample mean is nothing but the sum of each of the samples divided by n, where n is the number of samples collected. To help you see this more clearly, suppose I have only two random variables, x and y. Out of those two random variables, I create a new random variable z, which is the sum of x and y. Well, if x is random and y is random, then surely you would agree with me that z would also be random. For example, you flip two coins and you add up the result. Hence, the sum of random variables is also a random variable. In fact, any function of random variables is also a random variable. It turns out that if you have two random variables x and y, which are independent and identically distributed normals with mean mu and variance sigma squared, we can easily calculate the distribution of their sum. In fact, if we say z is equal to x plus y, then z also comes from the normal distribution. This normal distribution has mean 2 mu and variance 2 times sigma squared. If you're interested in why this is the case, I would strongly encourage you to go through the calculation to find the distribution of x plus y. Following this pattern, if we had summed up n different IID samples of x and called that z, then the distribution of z would be normal with mean n times mu and variance n times sigma squared. After a bit of algebra, you can show that the distribution of z divided by n, in other words, the sample mean, is also a normal, but with mean mu and variance sigma squared over n. Let's take a moment to think about why this makes sense. The mean of x is mu, so the mean of the sample mean is also mu. That's pretty logical. What about the variance? This also makes sense. It says that as I collect more and more data, the variance of the sample mean decreases. The more data I collect, the skinnier the distribution around the sample mean becomes. This also makes sense. Since the distribution of the sample mean is normal, I can plot the PDF of this distribution. From here, the confidence interval is obvious. As you know, the total area under the curve is 100%. The 95% confidence interval is simply the middle area of the curve that will cover 95% of that 100%. In other words, this leaves 2.5% on the left side and 2.5% on the right side. This is because 95% plus 2.5% plus 2.5% equals 100%. As an exercise, you might want to try this yourself using Python. Suppose that I have a standard normal, that is, the normal with mean 0 and variance 1. I claim that the point on the left boundary of the confidence interval is minus 1.96, and the point on the right boundary of the confidence interval is plus 1.96. Obviously, there is some rounding error, but these are convenient values which are usually used by statisticians. As you recall, these are called quantiles. If I pass in 0.025 into the quantile function, I get back minus 1.96. If I pass in 0.975 into the quantile function, I get back plus 1.96. Therefore, if I take the integral, or in other words, the area under the curve of the standard normal from minus 1.96 to plus 1.96, I will get 0.95 or 95%. Alright, so how can we relate this back to our estimate of the sample mean, which has mean mu and variance sigma squared over n? Well, it takes some algebraic manipulation and probabilistic reasoning, but if you write this down on paper, you should be able to derive this on your own. First, we can start with a fact that we already know, that x bar, our estimate for mu, has mean mu and variance sigma squared over n. This is the same as saying that x bar minus mu is normally distributed with mean 0 and variance sigma squared over n. So the mean has changed, but the variance hasn't. Of course, if you subtract mu from a distribution with mean mu, then the new mean will be 0. The next step is to divide x bar minus mu by its standard deviation. That's sigma over the square root of n. As you recall, subtracting the mean and dividing by the standard deviation is called standardization in statistics. And we know that the result is that this now has the standard normal distribution, in other words, mean 0 and variance 1. Using what we just found, we can express the 95% confidence interval as follows. We know that the 95% confidence interval is the standardized x bar we had before, with a lower bound of minus 1.96 and an upper bound of plus 1.96. Now all we need to do is rearrange this expression to isolate mu, the true mean. Once we do this, we obtain the familiar expressions for the lower and upper bound. The lower bound is x bar minus 1.96 times sigma divided by the square root of n. The upper bound is x bar plus 1.96 times sigma divided by the square root of n. One important thing to mention is that, in reality, we do not actually know sigma. Because of this, our standardized x bar must be expressed as follows, with the estimate of the standard deviation s, rather than the true sigma, which we do not know. Unfortunately, what happens when you include this estimate is that this random variable is no longer normally distributed. In fact, it's t-distributed. Luckily, we've already worked with the t-distribution, so you are comfortable with it at this point. The normal approximation is justified due to the central limit theorem, as well as a few other theorems which are outside the scope of this course. Basically, as n approaches infinity, the t-distribution approaches the standard normal distribution. In other words, what I'm saying is that even though our standardized x bar is t-distributed and not normally distributed, we will continue to use the boundaries minus 1.96 and plus 1.96. This is a justified approximation. Furthermore, I've played a little trick on you. What is the trick? Well, we started this lecture by assuming that our returns were normally distributed, but we already know that this is not exactly true. However, we can again apply the central limit theorem, since the sample mean is a constant times the sum of random variables, and as you know, the sum of random variables approaches a normal distribution anyway. This is actually a powerful approximation. It means that we can use the normal approximation for confidence intervals, the same one I just showed you, for any distribution, even coin tosses, which can only take on the values 0 and 1. As a side note, another common way to estimate confidence intervals in finance and time series forecasting is to use bootstrapping. The basic idea is we repeatedly draw samples from our own set of samples. It's an odd idea, but it turns out to work. We won't discuss this method any further for now, but be aware that there are other options if you'd like to research them on your own. Alright, so that concludes our lecture on how to calculate confidence intervals, which will be applied to our expected return estimates. To bring this back to the big picture, this is all part of trying to model returns. Previously, we looked at how returns might be distributed. Now we are looking at different ways of quantifying this distribution.